So you guys are asking me to talk about tangent of x, right? And so it says find the derivative of the inverse of that function. That's the assignment. Okay? Well, according to the inverse function theorem, and it says at the specified point, the inverse function theorem says that the slope of the tangent line of the inverse will be 1 over the slope of the tangent line at the original point if you plug it in the right way. And sometimes that's what we're having trouble with. Okay? So let me go ahead and talk about this. Well, again, let's use the calculator. So I'm going to punch the calculator up. And just as an example, here I go. Turn it on. Y equals. We're going to type in tangent of x. And you guys know what that graph looks like, right? It should be familiar when I press graph. Am I in the right mode? No, I'm in degree mode. What's that? It's a radian world. Let's do zoom trig. And let's press enter. And there they are, right? Hey, by the way, this function on the board, does it have an inverse? Remember what we talked about last time, the word one-to-one? Is this function one-to-one? Not at all, right? It doesn't pass which test? It doesn't pass the horizontal line test. Now, the television audience at home, you're missing this. But what I'm going to show the people that are here, that made the effort through the snow, is what we do when we want to graph the inverse trig function. We restrict the domain, and we say, hey, let's only look at the window between those two middle asymptotes. They're red lines on my board, right? What's that domain? We're going to restrict the domain and make it from where to where? You guys know what these asymptotes are at? Oh, so tangent of x, remember this, is equal to what? Sine of x over cosine of x. When will this function be undefined? Anytime that the cosine x equals, if the cosine x equals 0, and when does the cosine function equal 0? That on the unit circle happens like here at the point 0, 1, and also here at the point 0, negative 1. What angles are those? Pi over 2 and negative pi over 2. So what we do is we restrict the domain. This will be the domain from negative pi over 2 to pi over 2. So now what happens is I'm about to graph the inverse tangent. Inverse tangent of x. And like I said, I had to memorize what that graph looks like. You don't because you have a calculator. Although, the more you know, the better, right? So just like we restrict the domain of the tangent function, that is going to tell me what about the inverse tangent function? The range. What's the range going to be? Negative pi over 2, pi over 2. Okay? Now this seems like an awful lot, but I'm just trying to give you kind of a flavor of what the heck's going on here. So, turn the calculator back on. It says, look at the point 1 comma pi over 4. But that seems kind of backwards. It's like, why do we even talk about that? Well, the reason we talk about that is because on the regular graph, we can talk about, and let me calculate a value by hitting second trace. We can talk about the value pi over 4. There. Notice what's the output? 1. So the tangent of pi over 4 is 1. You guys with me? So over here, when I graph the inverse tangent function, I don't know very much what it's going to look like. I do know it's going to have an asymptote. I do know it's going to have an asymptote at negative pi over 2. Y equals negative pi over 2. I do know it's going to have an asymptote at pi over 2. And I know it's kind of going to look like the tangent function, except that what you do, remember you reflect along which line? The 45-degree line, that's right. Y equals x. Remember? Y equals x, because you're switching input and output. So take this curve, flip it over that line, and what's it look like? Well, let me show you. Come over here, and instead of graphing tangent of x, I'm going to turn that one off. I got to put it up here so you can see it. I'm going to turn off tangent x, and instead I want to graph inverse tangent x. And on our calculator, if we hit the second key and hit the tangent, it automatically does inverse tangent. And I just feel like most students coming into calculus aren't very familiar with this function. You haven't done it very much. This is actually where I think most students really start to learn about inverse functions. Well, let me graph it for you. You see? Are there asymptotes? Yeah, this time instead of vertical asymptotes, we have horizontal asymptotes. You see that? And why aren't there lots of them? Why don't you have lots of these things? Well, then it wouldn't be a function. So the reason we need a function to pass the horizontal line test if we want to talk about the inverse is because to be a function, it has to pass the vertical line test. Are you with me so far? Okay, next. What are we trying to do in this problem? Find the derivative of the inverse of the following functions. Well, okay. So really, hey, that actually works. Nice job, Paul. Well, not quite. 5 or 2 is a little high. But what I can do now is I can calculate a value for what's the inverse tangent of 1. And what should the answer be? Well, they say 0.7853. Is that pi over 4? I don't know. Let's check. Let me try. Oops. Let me try pi divided by 4. Yeah, 0.7853. It's working. Okay? So I'm starting to make sense of this inverse tangent function. All it does is switch input and output. So again, what we're trying to do is find the value of the derivative there. Well, luckily, your calculator can do it for us, guys. You ready? Here I go. Y equals, well, graph. There's the graph. And, you guys see that I can calculate values. Have you ever done this before? Choice 6. What does that do? It calculates a derivative. It doesn't take the derivative of the inverse tangent because my calculator doesn't know how to do algebra. Now, TI-89 actually can do that. It has a few memorized. Okay. But what I have to do now is I have to tell it which x value I want. So I want to type in 1. And it'll tell me the value of the derivative at pi over 4. Oh. Well, approximately. What do you think the value actually is? I think it's 1/2. It says it's 0.5000008. I think it's 1/2. I'd like to prove it though. Okay? So again, we need the inverse function theorem. And again, what it says is that the derivative, okay, so f inverse of 1 prime, the derivative evaluated at 1, or maybe how about I write it this way? Yeah. It's almost easier to say in English than it is in sentence. Find the derivative and evaluate it at that point. It will equal No. But do you know the derivative of the tangent function? Secant squared. So what I can do to do this problem is I'll say the answer is going to be 1 over the secant squared of pi over 4. Let's work that out. What's the secant of pi over 4? So what do I have here? 1 over the cosine squared of pi over 4, right? Does that make sense? 1 over cosine squared. Give me a way to simplify that. Cosine squared of pi over 4. What's the cosine of pi over 4? Square root of 2 over 2. Squared. That's what it means, right? When I put a 2 here, I'm really squaring the whole thing. And when I square radical 2 over 2, I get 2 over 4, which is 1/2. There's the calculation that you had to do for problem 43. And that's a problem that tells me, do you understand the inverse function theorem or not? So I hope that helps a little bit. These are the two, so far, these are the two formulas that are new to us. All right? So I think I'm going to start by having you quiz each other, make sure you know those formulas. Ready? Go ahead. Okay, so, back to our program here. We covered these things, and we also defined the logarithm last time, right? This is the log. What does that mean again? It's what kind of function? I call that an area function, right? It's area under which curve? The log function is giving me the area under what curve? 1 over 2. Right? There's little teeny pictures I have. Look at those pictures from last time. Right? Those are there. Okay. Now, one thing we didn't do last time is we didn't remind you of what are called the log laws. When you study logarithms in algebra, the reason you study them is because they have these really nice properties that kind of let you get at exponents, okay? So here they are. I just want to remind you of them. Okay? The log laws. So number 1, if I take the natural log of, say, A, okay, times B, where that's a product, how can I rewrite that? Yeah. It turns out that the natural log of a product is equal to the sum of these natural logs, okay? Number 2, once you have that, you might believe number 2, the natural log of a quotient, it's the difference. Yeah, take the natural log of A minus the natural log of B. And number 3, natural log of, and this is the most powerful of the natural logs, take x to some p power. And what's that the same as? P times the natural log of x, right? Now, one question you might have is, where do these log laws come from? Because, by the way, how many are familiar with these log laws from another class? Let me ask that. Okay, fine. But here's the thing. In the other class, they didn't tell you that the log was some area function, right? They did not say natural log of x is an integral. No way. You never saw that before, right? So where do these laws come from? Maybe they just gave them to you? What they probably did is they talked about exponential functions, then they talked about logarithms, and then they kind of used properties of exponents to talk about these. Okay? But we're approaching this from a different angle. We're saying this is an area function. Why would these things be true? All right? Now, I think they're proved in your book,
I think the only one I want to do is the third one. I think that might be worth our time, actually. All right? So let's suppose we're thinking about the natural log of x to the p. Well, what do? According to our new definition, if I have the natural log of x to the p power, I can put that in parentheses to kind of make it clear what I'm doing. Well, what does that equal? It's the integral from 1 to x to the p power 1 over t dt. Right? That's what it means. Where it used to say x, I'll put x to the p power. But how am I going to get that that's the formula? I'd like to take the derivative of both sides of the equation. I'd like to do that next. That's my hunch on what to do. Because I think you guys last class learned how to take the derivative of this side. The derivative with respect to x of this side, well, see, that's my u. My u here is x to the p power. So it's going to be 1 over x to the p, 1 over u, times what? Yeah, the derivative of x to the p. So it's 1 over x to the p times, yep, p times x to the p minus 1, right? So that's what it equals. So that's that derivative. So what's that equal? Well, you could write this side as a fraction by putting it over 1. Right? Can you cancel anything? Well, I see a p up here. I can't cancel that. But don't I have a whole bunch of x's in the numerator and a whole bunch of x's in the denominator? So I start canceling them. Do they all disappear? Almost, though, right? There's one left where? Where's there one extra x? In the numerator or in the denominator? Sure, it's x to the p power. This one's x to the p minus 1. So if I cancel all the x's, I get that the derivative of the natural log of x to the p is p over x. Right? Okay, so that's interesting. What if I take the derivative of this guy? Well, if I take the derivative of that guy, so I took the derivative of the natural log of x to the p, and I got p over x. This is by taking the derivative. If I take the derivative of p ln x, what do I get? Don't you get p times 1 over x? Right? P is a constant. So they have the same derivative. Does that mean that the functions are the same? Well, almost. It almost means that. We learned from the mean value theorem that if you have two derivatives are the same, you could take the antiderivative. We know the antiderivative of this is the natural log of x to the p. We know the antiderivative of this is p ln x. And they're the same except that maybe there's a constant on one side, right? Maybe there's a constant on one side. And now all you do is you plug in a really nice x value. So a really nice x value would be substitute in x equals 1. And I get the natural log of 1 to the p power is p times the natural log of 1 plus c. And why is 1 such a nice thing? What's the natural log of 1? No? Remember what the natural log of 1 is? I'll give you a hint. Plug in 1 for x right here. It's going to be 0, right? The natural log of 1 is 0. So this is 0. And what's 1 to the p power? That's 1. So this is 0. So that shows c is 0. And that's a proof of the third log law. Because if c is 0 in this equation, now we have the third log law works. Okay, enough of that. We have log laws. We can use log laws for finding derivatives, and it really, really helps. And that's kind of the point of the next two examples. So here I go. We did this one. We did this one. We did not yet do this one. Write it down. Let's find the derivative. If you're going to find the derivative of that one, you probably want to rewrite the function. Actually, you definitely want to rewrite the function, right?
First of all, that square root, what am I going to do with that?
Okay, we can. We can break it up into two. We can write it as the natural log of 4x plus 3 to the 1/2 power divided by 6x plus 3 to the 1/2 power. That's actually a good idea, Dan. Ah, the log law. Thank goodness. Because if I didn't do that, I could do 1 over this big ugly fraction and then times, you'd have to do quotient rule, you'd have to do lots of, you guys see how ugly this would be? There's no way I could finish it on the amount of paper I have left. But what Jocelyn suggests, using a log law, is a good idea. Go ahead, Jessica, question. Did I? Then we're dead. Let's see. 4x plus 3 over 6x plus 1. Thank you. Anyone out there in the E world see that? No, because you weren't here. All right, so we're here. So what we're going to do is use the log laws, right? Jocelyn says, hey, let's write this as the natural log of 4x plus 3 to the 1/2 power minus the natural log of 6x plus 1 to the 1/2 power. In my mind, that's log law 2, right? The way I have them numbered, right? Anything else I can do before I start to take the derivative? Bring those 1/2s out front. 1/2 natural log of 4x plus 3 minus 1/2 the natural log of 6x plus 1. That's a great move. A great move. What would have been a problem that's really difficult now becomes a problem that's really not very difficult. Let me work it out. dy dx equals 1/2 times, now let me do the first one here. It would be 1 over 4x plus 3, because it's always 1 over u, times du dx, so times 4, right? I wrote it as 4 over 1 because I'm going to simplify it eventually. But are you guys with me on this? The reason I multiply by 4 is because I have to multiply by the derivative of what's inside. That's the chain rule. Here, you guys try the other piece. So minus 1/2. See if you can write down what the rest of the derivative is for this problem. So we did you guys do this? 1 over 6x plus 1 times 6, right? So final answer for this one would be, here I'll write it down here in green, dy dx equals, I guess I would write 2 over 4x plus 3 minus 3 over 6x plus 1. I can't really cancel anymore. I don't want to try and add those, subtract those fractions. I would probably just leave it like that. You guys follow? Pretty amazing that you could do that derivative in such a short amount of space. but I owe it all to the log laws. Okay, so that demonstrates why the log laws are useful. But then what comes along, and this is really cool, is somebody at some point realized these log laws are so powerful, we should use them more often. For example, here's my last logarithm derivative. I want to teach you a technique here. It's called logarithmic differentiation. Okay? And I'm going to use it on an example, but before I do, I want to explain kind of what you do. So given a function, what you do is you first take the log of both sides, and then take the derivative. Okay? So here's the game. I have y equals f of x. And again, this is how I'm going to do, it's called logarithmic differentiation. So what I do is I have some function, and I didn't even name it yet. But what I do is this. I take the log of both sides. ln of y is equal to ln of f of x. It's still a true equation then. I just did the same thing to both sides. Now take the derivative of both sides. Actually, you know what this is like? Do you remember when we did what's called implicit differentiation? That's really what we're doing here. But we're first of all taking the log of both sides. Now, what happens on the right is you get stuff. What happens on the left is I always get the same thing. I get, what do I get? What's the derivative of the natural log of y? 1 over y times dy dx. That's right. Now again, the goal was we want to find dy dx. That was the goal. Well, the answer is this. dy dx will equal stuff times y. Or stuff times the original function. That's how it works. So why would we do this? Because in order to compute the derivative of stuff, you can use the log laws. And that really pays off. And so the example I'm going to show you is here on the screen. Right here. You see that? If someone tells you to take the derivative of that, you start crying without a new technique, right? You say, no, I can't. It's going to take me the rest of the paper. And it still might, actually, because it's actually not an easy problem. But we're going to tackle it using logarithmic differentiation. So here I go. I have y equals, holy mackerel, how am I going to write that? Well, wait a minute. That numerator, can you give me a better way to write it? Let's write it as x cubed plus 1 to the what? 3 halves power. Does that make sense to people? Write it as x cubed plus 1 to the 3 halves power. Divided by, and I think it's x squared plus 1. Yep. To what power? To the 4/3 power. Yep. So that's how we're going to start this problem. And when you see a function with exponents, that's kind of a dead giveaway that, maybe I should use logarithmic differentiation. That would help here. So what's it mean? The process is, do what to both sides? Take the natural log. So natural log of y is equal to the natural log of ugly fraction. So the natural log of y is equal to, haha, here's where it pays off. You use log laws. Now I'd like to use, last time I did this, I did it in 2 steps. I'd like to use both log laws in the same step because, well, we have a lot to do today. And I think you can handle this because you guys are, well, heck, if you can get through the snow, you can handle a lot. How many are with me up to here? Okay. I did the subtracting one and I did the bringing the powers down. And that's what logs are good for. You get those exponents out of there. Okay, next step. What are we going to do to both sides? Well, we're going to take the derivative of both sides, right? And when we take the derivative of both sides, on the left-hand side, I get 1 over y times dy dx. Okay, that's taking the derivative. On the right-hand side, I should pause and let you guys write down what you think we get. I should. So let's see, I have 3 halves times 1 over x cubed plus 1 times 3x squared. That's how I do the first one. Is that good? Minus 4/3 times 1 over x squared plus 1 times what? 2x, right? Okay, so 1 over y times dy dx equals, boy, what would this be? I guess 9x squared over 2 times x cubed plus 1 minus 8x over 3 times x squared plus 1, right? So if you want dy dx, there's only one thing left to do to both sides of the equation. Oh, I guess because I know that if I actually wanted to subtract the fractions, I'd have to find a common denominator, and that would be 6 times x cubed plus 1 times x squared plus 1, and that'd be harder for me to figure out if I distributed it through. So I would leave them apart, because if you actually wanted to subtract the fractions, that's what you would need to use all the factors. I don't really feel like simplifying it anymore. No, I'm getting tired of this problem, and I'm almost out of paper. So I'm almost done. But I'm not done. Why? Because I didn't get what by itself yet. dy dx. If you have this equation, what do you have to do to both sides to get the dy dx by itself? You need to multiply both sides by y. Well, what is y? Y is what we started with. It's not even on the screen anymore. That's how long this is taking. See it? It's that big mess. So you want to know what your final answer is? Here it is. Final answer is all this stuff in blue times x cubed plus 1 to the 3/2 power over x squared plus 1 to the 4/3 power. I guess I'll write it down. 9x squared over 2 times x cubed plus 1. By the way, Jocelyn, you did have a good question. Another reason not to multiply by 2 is if I distributed this fraction, I can see I could cancel a little bit. But again, I'm tired of it. You're tired of it. Let's just leave it. Do you guys understand the process, at least? It's interesting. The original function didn't have any logs. But by taking the log of both sides, I actually came up... Can you imagine coming up with this answer? Like just taking the derivative the way you did on the second or third exam? Eesh. That'd be nasty. This makes it manageable.
The inverse of natural log of x is going to be e to the x.
talked about the number e. E is the number that, if you take the natural log of it, you get 1. That's the definition. Actually, your book actually gives that as a definition. Right here, down a little bit, mammoth section. Correct me. Here's all the log laws, and then they say, we can talk about the exponential function. Oh, that's what I was going to ask you guys. Did you guys work on the quick checks yet for this section? Should we talk about any of them? Yeah? Like, I mean, even quick check 1, I noticed. They start talking about this function, the natural log of the absolute value of x. Did that bother anybody? It's right before it. They say the derivative of the natural log of the absolute value of x is 1 over x. Why? I mean, how do you do that? Well, when you find the derivative of a function, right, we know the derivative of the natural log of x is 1 over x without the absolute value bars. Why would it have the same derivative? Well, the key is really here in this quick check. They say, what's the domain? X can be, see, the domain of the original natural log function is x is greater than 0, right? Here, the domain is almost anything. Anything except what? 0. Why is that important? Well, they show a graph coming up. Let me find it. Yeah. Let's see. Oh, because they hide these. Found it. Well, here's the graph of natural log of x. But the natural log of the absolute value of x is defined all over the place, right? Now, it turns out, why would you have kind of a mirror image? Well, remember 1 over t? 1 over t, you had a mirror image over here. But let me plot the derivatives, right? Here's 1 over t. But it's negative down here. You with me? It's negative. So anytime you're talking about the derivative here being the area, it's negative area in a sense. So that works out fine, right? The derivative of this stuff is negative, and the derivative evaluated over here is positive. And that turns out to be kind of nice and important because we're going to be doing antiderivatives of logs pretty soon, and the absolute value is going to come back to haunt us, okay? I just wanted to throw it out there. Which is even? Yeah, if you put absolute value in there, it's definitely an even function. That's right. That's absolutely right. So it's kind of funny. You look at number 7. They say, hey, here's a formula for the antiderivative of x, of 1 over x. Remember that one? That's the one we couldn't do, right? Well, anytime you have a derivative formula, you also have an antiderivative formula. And so we will write natural log of, you're always going to write absolute value of x when you do an antiderivative of 1 over t dt. Why? If you didn't, we'd run into problems when x is negative. Now, when's the only time we would have a problem? But we would have a problem over here when x is 0 too, so we're not going to worry about that, right? This formula turns out to be really nice, and that's why they talk about absolute value. Okay, but it's time to talk about the exponential function. And they say, hey, natural log, here's the graph of it. Oh, question. Go ahead, Jocelyn. Yeah, did I pass it? It's coming up. Yeah, I'm going to do it. Okay? So here's the natural log function. Right? Remember what we said the natural log of 1 is? 0. That's good. And if you integrate from 1 to something bigger than 1, you get a positive area. And we said that if you integrate from 1 to something smaller than 1, that's negative area. So that's why the function looks like this. Okay, here's y equals x. So
This, by the way, this is a funny way of writing e to the x. If you ever do it in computer language, that's what people usually write. exp means exponential of x. And it's just the inverse function of the log function. Okay. Getting towards Jocelyn's question. What they're doing here is they're doing all kinds of nice formulas. But they keep writing exp. I think if I just write e to the x, I think you'll be very happy with some of these formulas. Okay? And they're going through a whole discussion. This is pretty technical here, okay, I think. So I'll just write a little bit down using e. They say, okay, suppose you have e to the x1 plus x2.
E to the x1 plus x2. And they say, what would that equal? And what they just worked out is that that's the same as e to the x1 times e to the x2. It's funny, though. I usually write it the other way. I usually write, hey, if you multiply two things, what do you do with the exponents? There they are. Right? These are your old rules about exponents. Or what if you have e to the x to the r? What do you, yeah, you multiply those exponents. And what if you have e to the 0 power? Why is that true, though? Why would e to the 0 equal 1? Because the natural log of 1 is what? 0. So they're basing all their properties of the exponential function on the fact that it's an inverse of the log function. They started with the log. Okay? So that's kind of, these are the kinds of things that they're talking about right before Quick Check 3. All right? So now let's see if I can answer your question on it. Not this one. Quick Check 3 says, where is it? Nope. Nope. Where is it? Here's all the properties I was just doing. Is it down here? Past the limit definition? I did this last time with you guys. Okay. Simplify these guys. Okay, that's it. That's a very good exercise. So when you have e to the natural log of 2x, I want you to understand that these functions are inverses of each other, so they undo each other. Okay? E to the natural log of 2x. That's just 2x. It might be a little clearer if you write it the other notation. exp is another way to write e to the. That's what I like to say. E to the. So we're going to actually sometimes take e to the both sides. Right? So these undo each other. You get 2x. They're inverse functions. Also, if I had the natural log of the exponential function of 2x, what does that equal? 2x. Well, let's write that using the e to the notation. It would say natural log of e to the 2x. What does that equal? 2x. So I think this is just getting you used to the idea that what you have here are inverse functions. So again, this is Quick Check 3. Here, let me go ahead and do the other ones. Oh, funny, I just did the other one. Now there's two more I should do. I should do e to the 2 ln x. That's actually a really nice one to see. Good exercise. And then they also want me to do the natural log of 2 e to the x. Okay, we'll see if we can do that. By the way, did anyone get these? That's one way to get it. There's other ways to do it. Maybe I'll show you another way also. What Jessica did is she took the 2 and said, hey, I'm going to put it up there. So this is e to the ln of x squared, right? And e and ln undo each other, so what's the answer? X squared. Very nice. They're inverse functions. What about this one? I'm going to let you talk to each other for 1 minute about that one. This time I'm going to use log law 1. The natural log of a product. Log law 1. I saw somebody try to take the 2 and put it up here in an exponent. You can't do that with an e, okay? I actually saw more than one person try that, okay? But you can do this. What's the natural log of a product equal to? It's equal to a sum of logarithms. There we go. Now what's the answer? Well, this is natural log of 2 plus what? X. Probably the book would write x plus the natural log of 2. I don't know why. I just think that's what they would do. Is that what they did? I'm curious. Here, let me check. What did you guys write? No, they put natural log of 2 plus x. All right, fine. Good. Good question. Especially with the questions you guys asked today. What is the slope of the curve y equals e to the x at x equals natural log of 2? Let me draw a picture of that. So this is quick check 4. This is really good for us right now because of the questions you guys asked me today. So I know y equals e to the x. Okay? So again, we want the slope at x equals ln of 2. And again, I guess I could use a calculator to do that. I just think this is worth looking at. Here's the okay, let me go here. Let's get rid of these and type some really nice functions. So I'm going to type, to get e to the x on the calculator, you guys know how to do it? Second ln. That actually makes sense. It says e to the. Yes, it's exp. On a computer, you probably write exp. On a calculator, you get e caret, right? That means exponent. So e to the x. And then I also want to, just for the fun of it, graph ln of x on the same picture. There they are. You know what's kind of weird? If you graph y equals x here, you might want to do that just to kind of see the inverse relationship. But it might not look like a 45-degree angle to you necessarily. It depends on the zoom. If you really want it to look good, you can hit zoom square. Because your screen is a rectangle. This will give you square graph paper. It'll make it look nice. Yeah, that's just something you might try if you don't like your picture. Okay. So what I'm supposed to do here is put in, let's do this. Let's calculate the value at the natural log of 2. Natural log of 2. Let's see what the value is. Well, it says y equals 2. Actually, I should have known that, right? That's what we did on quick check 3. So, in other words, if I'm sketching a graph, which is what I want to do right now, of y equals e to the x, it looks like this. This is the axis. I know it goes through 0, 1. I know that it takes off. This is called exponential growth. That's what makes it so important to applications, actually. How quickly it grows. And I know that it goes through, right here, this is the point, natural log of 2 comma 2, which is about 0.69, it looks like. 3, 1. Yeah, okay. Well, what we want is we want the slope of this tangent line. So what's the slope of that tangent line? I don't know. Well, I do know. Do you guys know the derivative of e to the x? How do you know? Well, I told you, that's why. Yeah, I gave away the show weeks ago because I was too excited. Let's suppose we didn't know what the derivative of e to the x is. If we didn't know what the derivative of e to the x is, and our book doesn't think you know it yet, because our book doesn't know that I told you, what could we do? We do know the derivative of which function? Dun, dun, dun. Y equals, I'll call it y inverse. What's that? The natural log of x, right? So if you want the derivative of this blue, okay, we want that slope. I'll tell you, by the inverse function theorem, this slope equals, oops, my calculator's in the way. By the inverse function theorem, this slope equals 1 over the derivative of ln of x evaluated at x equals, oh, what's the right x value to use? 2, that's right. You use 2. So let's work it out. We get 1 over, guys, what's the derivative of ln of x? 1 over x, evaluated at x equals 2. So that's 1 over 2, that's 2. So that's the inverse function way to do it. That's what I think they wanted you to do. But I have an easier way because I told you the formula already. I gave away the show. What's the derivative of e to the x? Yep, gave it away. And since you know that, you could find the slope of that tangent line in the following way. Just do e to the what? What do you have to plug in for x? ln2. And what's e to the ln2? 2. So I see two different ways here that we can come up with the same result. Just depends if you know what the derivative of e to the x is or not. And I told you already. Find the derivative of this function. F of x equals x e to the 2x minus e to the negative x. So here I go. I want to find the derivative of this thing. Well, what rules am I going to be using in this example, guys? Yeah, pretty much, right? Like here, just to find the derivative of x e to the 2x, what rule comes to mind right away? Don't you think product rule is there, right? So I have to do u prime v plus uv prime. Let me try that. When I do u prime v, I'm going to have 1 times e to the 2x, okay, plus x, because that's what u is, times what? What's the derivative of e to the 2x? Well, e to the 2x times what? Dong! Times 2. That's the chain rule. You have to take the derivative of what's inside. But remember, some people don't like this right here. Well, another way to do it is to say, you know, what I really have is exp of 2x. I was taking the derivative of that. Well, what is that? It's exp of 2x times the derivative of what's inside, 2. That's where that comes from. It's what's inside the parentheses. Let's see if you guys can get the rest of this. So it would be minus the derivative of e to the negative x is e to the negative x times what? Nice. Times negative 1. Again, that's the chain rule being used. It's funny. I feel like by the end of this section, you will feel like you finally understand the chain rule. That's my hope. Might take till next Wednesday, but I think that's what's going to happen. Let me finish the problem by simplifying it. I get, let's see, e to the 2x plus, here I would write 2x e to the 2x, and here, what would we write? Probably plus e to the negative x. Is that okay? And back of the book might do this. Sometimes I've seen them do this. Factor out e to the 2x or something like that. But I kind of like this answer. Okay. All right, next example. Well, examples. Here we go. Oh, this is one of my favorites. F of x equals e to the x plus e to the negative x over 2. Okay. So we'll let you guys try to find the derivative of that. Oh, please don't use the quotient rule. Don't. That's the hard way to do it. You could, but I think the easier way to do this is to think of this as 1/2 of e to the x plus e to the negative x. Okay. Anyways, I'm going to have you guys find the derivative, f prime of x, and I'm going to have you guys find the second derivative, just for fun. All right, if you finish the first one. And we'll see how long it takes you. Ready? Nope. All right, here we go. What'd you guys get for f prime of x? Well, you kept the 1/2 here. And then you probably wrote this. Well, what's the derivative of e to the x? And then did you guys write minus e to the negative x? Right? Good. And then what's the second derivative? 1/2. It's what you started with. Right. This, by the way, is sometimes written e to the x minus e to the negative x over 2. Right? That would make sense. And then, yes, you get back what you started with. Now, these have really nice names. Beautiful mathematics that a lot of times we don't have time to get to. So I want to at least show you. This function has a name. It's called the hyperbolic cosine. And people write this for short. Hyperbolic cosine of x. And this function is called the hyperbolic sine of x. So let me ask you guys, what's the derivative of the hyperbolic sine of x? What's the derivative of the hyperbolic sine of x? It's the hyperbolic cosine of x. What's the derivative of the regular sine of x? Regular cosine of x. So that's kind of nice. And actually, the hyperbolic functions are even nicer, because the derivative of regular cosine is negative sine, right? But the derivative of the hyperbolic cosine is what? A sinh, right? I like to call that sinh and cosh. I just always did, I don't know. So those are really nice functions. And I remember studying those quite a bit. And we use them in differential equations, but we won't have time to do the whole section on it, I don't think, unless somebody does it for a project. So just thought I'd throw it at you. Okay. Here's just a few to try, guys. We're going to do some antiderivatives. Well, I got to practice going the other way. So we're going to integrate e to the 3x dx. What technique do you think I'm going to need for all of these integrations? Well, that's a good guess. But we're not going to use log logs. No logs here. Don't need it. Nope. There's a technique of integration that we worked really hard on. I told you it's the most important thing for Calc 2. see it really stuck with you guys. Thanks, guys. I try. It's called substitution. It's the chain rule backwards, right? So you're going to let u equal something for this first one. Any idea what I might let u equal for the first one? Nice. How about for the second one? Let u equal what? X over 4, right? This stuff in parentheses, right? Another way to write x over 4, by the way, is what? 1/4 x. Maybe that makes it easier. Anyways, whenever you compute u, the very next thing you should compute is what? Du. So what does du equal in the first one? 3 dx, right? And I don't quite have that. I just have dx. Dx, I guess, is equal to what? 1/3 du. So when I do the first problem, I would immediately change it to e to the u du, but what do I have to put out front? 1/3. So this then is a really easy problem. You get 1/3. What is the antiderivative of e to the u? Sure, e to the u. Plus c, I'll say. And so the answer to the first problem would be 1/3 e to the 3x plus c. Okay? And I think I should pause and let you guys try the next two problems. Because if you can do those, then we're making some progress. I'll pause for a minute. So let's see. If you guys did this one, you get du is 1/4 dx. So dx is 4 du. So you need to multiply by 4 when you do it. You have the antiderivative. Well, 4 times, again, e to the u du. That's another way to write e to the. So the answer is 4e to the 1/4 x plus c. You guys getting this? How many people got that second one? Do you guys have any questions? Got it? Okay. Yeah. And the third one here, I just said, hey, put any number up here you want, m. I don't care, as long as it's not 0. If it's 0, then you're just integrating 1. That's boring. But what's the answer going to be? Can you tell me? Well, it's going to be, just by kind of recognizing the pattern, you're going to get back e to the mx, right? But then you have to put something out front. What is it you're going to put out front? That's right, the reciprocal of m. You could go through the substitution and check it, but that's what it's going to equal. Okay? I should show you this last one. I got a minute, and I should do it, because otherwise there's just a headache here bound to happen. Here, let me show you. Last one. Boom. We have to try this one, guys. And I think we'll start with it next time, like I said, but the question is, what do you let u equal? That's the hard part. This is one of those where you'll try it, and you'll try it again, you'll be like, man, and then if you actually discover it, it's really cool. But I guess I just wanted to, since you've never seen one of these before, I wanted to give it to you as an example. Okay? So watch what I'm going to do. Let u equal e to the 2x plus 3, the whole denominator. Now, what does du equal? E to the 2x, almost, times, bong. I need to take the derivative of that, right? So what do I get? 2 dx, right? So I have e to the 2x dx sitting up there. It equals half of du, if you want. So now I'm ready to substitute. With all that stuff going on, I'm ready to substitute. So all this thought goes into transforming this into the following integral. Where it used to say e to the 2x, I now have a 1/2 du. It used to say e to the 2x dx. And where it used to say e to the 2x plus 3, I have u. So really, this is 1/2 integral of du over u. That's one way it's written. Or it's sometimes written 1/2 integral 1 over u du. Hey guys, what's the antiderivative of 1 over u? No? Yes. Well, ln of u plus c. Guys, I need to do one more thing to get Jacob to be completely right. I told you this, but you've never practiced it. I need to put absolute value bars. Now it's completely right. So wait a minute. Oh, I'm over time. That's not fair. ln of e to the 2x plus c. I'll finish it next time. I'm almost done. But at least you saw the substitution. Okay.
Done. We'll finish it next time.